Welcome everyone. For today's prep, we're going to start to look at p-series. So this is a very common type of series that we're going to encounter. So we want to spend some time on this. So first of all, what is a p-series? Well, they're related to power functions. So you can kind of think of it as p for power function. And what we have here, let's read through what the definition is. P-series is a series of the form, we're going from sigma n equals 1 to infinity, and the terms we're adding up are in the form 1 over n raised to the power p. So to kind of get a feel for what this thing might look like, if we write out the first few terms, our starting index is 1. So when we plug 1 into this formula, we get 1 over 1 raised to the power p. And then when n is equal to 2, we get 1 over 2 raised to the power p. And then when n is 3, we get 1 over 3 raised to the power p. And with this series, what we're attempting to do is we're attempting to add all those values together. All right, so the major thing we're going to have to do when we recognize that our series is a p-series is we want to figure out what that p-value actually is. So we want to identify that p-value. And it's going to be a constant. All right. And this p-series is going to converge or diverge based on the value of p. And we're going to look at the proof of this a little bit later. But for right now, we're kind of stating this, and we'll get to the proof. So we're just stating this result. So a p-series converges if that p-value is greater than 1. And it diverges if that p-value is less than or equal to 1. So, unlike geometric series, so geometric series is another very common type of series that we've looked at, and geometric series are very nice because we actually have a nice formula for what the sum of the series actually is, if we know it's convergent. P-series, not so much. So some of the sums are actually known. So as an example, if we're looking at the p-series with p equal to 2, you can actually prove it. It's very difficult, but you can prove it that sum is equal to pi squared over 6. So, in some cases, the sum is actually known for a p-series, but in a lot of cases, we're primarily just going to be interested in knowing whether the series converges or it diverges. So we're not going to actually be able to get the sum value in most cases. All right. And so these p-series, there's one special case that shows up, and we sometimes give this a different name as well. So there is a special case. And that is, we're looking at sigma n equals 1 to infinity, and this is when p is equal to 1. So the sum, the series is 1 over n, the series sigma 1 over n. And this is, if we were to write out the first few terms, just to get a little experience, this would be 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on. And this series actually diverges. So this is a p-series with p equals to 1. So it diverges, but it shows up enough where we give it a special name. So we call this a harmonic series. So you might hear me call it during class the harmonic series. And it's really just a special name for p-series with p equal to 1. All right. And as before, as usual, we can relax the starting index value. So the way we have this written is we're starting at n equals 1. We could start at n equals 2. We could start at n equals 3. We could start anywhere, really, and we'll be dealing with a p-series. positive integers. We don't want to start at n equals 0 because this would be undefined then. So any positive integer, 1, 2, 3, we'll still call it a p-series. All right, so we're going to come back and we'll do this part in class where we compare this to geometric series. So these are going to be our two kind of go-to basic forms of basic series later on. So we'll kind of review over those. And kind of give a little preview of things to come, we've looked at p-form improper integrals. So we've looked at the improper integral from 1 to infinity of 1 over x to the power p, and we proved some of it in class, that these types of improper integrals are convergent when p is greater than 1 and divergent when p is less than or equal to 1. And looks very similar to the type of series we're going to be considering here, and the result even. And we'll see later on that there's a special test called the integral test that relates series and improper integrals together. So sometimes, if we're investigating the convergence or divergence of a series, we can actually relate it back to the improper integral. But in any case, let's look at a couple examples. So we're just going to get a little practice working with this result. So what do we have here? Let's look at the first example. We want to figure out if this series is convergent or divergent. So it's a p-series, and we want to figure out what the p-value actually is. So that's kind of the first thing. So it's a power function, 1 over n raised to the power 2, and it's that exponent, that's our p-value. So when we write out our explanation and we state whether it's convergent or divergent, there's a few things we're looking for. So first of all, this is a p-series. We want to state the actual p-value. So in this case, the p-value is 2. And then we want to state the conclusion. So it's convergent. And the necessary inequality. So since our p-value is greater than 1. So these are really the four things we're looking for when we're dealing with a p-series and you write out your explanation. So want to see that you're stating that it's actually a p-series. State the actual p-value. And then the conclusion and the inequality that allows you to make that conclusion from our result. So this is an explanation that kind of gets it all. All right, so let's try another example. The sum from n equals 1 to infinity, 1 over square root n. So this is not quite written in the right format, so we could rewrite this, or maybe you just do this in your head too. But we could rewrite this as 1 over n raised to the 1/2 power. And once we get it like that, we can see what the p-value is. So this now is written in a p-series format. So this is a p-series. And we can see that the p-value is 1/2. So now we have enough info where we can say, is it convergent or divergent? And it allows us to, because the p-value here is less than or equal to 1, we know it's divergent. So again, when you're writing out the explanation, state what type of series that you're working with. So it's a p-series. State the actual p-value. So in this case, it's 1/2. And then state the conclusion. So it's divergent. and then state the inequality that allows you to make that conclusion. All right, so we'll do a little bit more practice with this in class, and then we're going to start getting into a lot of our different series tests. So this integral test idea is kind of a preview of things to come. So we'll see you then. Bye-bye.